Okay, we're all set. So, first of all, Markus, thank you very much for accepting the invitation. For today's seminar, Markus Aspelmeyer will, from Vienna, from QISS, will talk to us about the role of gravity in tabletop quantum experiments. I remind the format of the talk in case that you're not aware. It's usually 30 minutes. We advise 30 minutes slide presentation. It can go longer. It's to the discretion of the speaker. In order to leave enough time for discussion, usually we discuss about 1.5 hours after the talk. And Markus, if you're ready, you can go.
Thank you very much. Thanks for having me. It's really a pleasure because I like the format a lot. Of course, the format also means that I will leave out a lot of things. But since the discussion is longer, I'm more than happy to provide details, background references, and so on, and maybe also discussion other topics as is required. So I chose to briefly talk about gravity in tabletop quantum experiments, and let me start right away, since it's a short presentation, with the summary of the talk. So you can set your minds already towards it. So the summary essentially is, right now, to date, we have a few tabletop experiments that probe the interface between quantum physics and gravity. I will give you a very few examples. I will leave out many, but upon request, I can provide many more. In all of the experiments to date, it's gravity, either from Earth itself or from other macroscopic source masses, acts as a constant classical background field, if you want, as a classical gravitational source. So loosely speaking, in these experiments, the quantum systems that are being used in these experiments are essentially test particles in an external fixed space-time metric provided by some classical source mass, which is either Earth or kilogram scale or other earthbound gravitational sources. Now, on the other hand, and I will go a little bit into detail here, if you look at the last 2 decades or so, there has been tremendous progress in controlling the quantum regime of solid state objects. And I will show you a little bit what I mean by that and where the status at the moment is. And of course, this you can now extend, and such sort of quantum control of solid objects may lead to a new class of what I call gravitational quantum physics experiments. So experiments in which the quantum system itself may serve as a gravitational source mass. So this is a realistic perspective for such experiment. And here I put already a question mark. So is it? Hopefully, because there are extreme experimental challenges, because there are extreme requirements combining large mass of a quantum system, meaning that you also need long coherence times. And I will show you, giving just current state-of-the-art experimental examples, this is really a super challenging task, and that I would say statements in the literature of feasibility in the near future of such experiments is a little bit exaggerated, but it's not hopeless. So yeah, I'm just saying that it's really hard, and I will show you why. And on the other hand, of course, there's an interesting conceptual challenge that goes along. Namely, maybe we can find less demanding and yet similarly powerful or meaningful tests to probe how gravity reacts to quantum source masses. And this is a challenge that I really would like to put out to everyone, because this is not a lab-based challenge. This is really a conceptual challenge. So let me start. When we talk about gravitation, gravity has always been exceptional in some sense. So it came as a big surprise several centuries ago to some people that gravity would also apply to earthbound objects and not only to celestial objects. So it was eventually triggered by some conjectures of Newton about the density of the Earth that Earth-based experiments of gravity started. There's a famous experiment by Maskelyne in the 1770s that tried to measure the gravitational attraction of a mountain using pendula that they were going around this mountain in Scotland and were trying to measure the gravitational attraction of such a pendulum towards the mountain, and basically they were trying to measure the deflection with respect to the fixed star horizon. Then this measurement campaign was not fully successful, but it inspired Cavendish to conduct high precision laboratory-based experiments to measure the, well, at that time it was called measuring the density of the Earth, but eventually measuring the gravitational force of lab-based source masses. And we know how that went. Now, if we fast forward a few hundred years now, we know also that quantum systems basically started to spark in experiments, and they are, of course, extremely good, excellent systems to test small forces, which then, oh, I apologize, basically, of course, you're all aware of that. If you fast forward to today, classical Cavendish experiments are now really made to perfection, for example, at the University of Washington by Jens Gundlach and Eric Edelberger in these famous Erdwash experiments, where they can now measure Newton's constant to a precision down to 5 digits, which is the best value for the gravitational constant that we have to date. And this is essentially a Cavendish experiment made to perfection. Now, quantum systems entered, and with quantum systems, the question was, of course, how do quantum systems couple to gravity? And this is something that for which we have working theories. So we have many, many beautiful experiments now, experimental examples that can all be well understood in the framework of standard quantum theory in a fixed curved background space-time, for example. Okay. Now, here I just give you 2 examples, two of my favorite examples. This was the famous cow experiment here by Kulela, Overhauser, and Werner, named after the initials of the authors, that probe the impact of Earth's gravitational field on the wave packet of a neutron. So in short, when you have a particle that traverses through a classical external field, it picks up a phase, a dynamical phase that is proportional to the action it acquires when it traverses through the field. You cannot measure an absolute phase, but you can measure phase difference. So if you now have the neutron and send it on the lower left here, you have the neutron and send it through an interferometer, you essentially split up the wave packet, and it now acquires, when it travels through different heights of the gravitational fields, it acquires a different dynamical phase, so it acquires a phase difference. And when you now rotate the interferometer in Earth's gravitational field, thereby changing the potential difference between the 2 arms of the neutron in the 2 neutron paths, you get a gravitationally induced interference fringes as a function of this rotation angle, therefore the height difference. So this was the first experiment that probed the impact of Earth's gravitational field on the wave packet of massive particle. And so it also and was essentially also the basis then for many follow-up experiments. So for example, Kasevich and Chu then pioneered atomic fountain experiment that increased the sensitivity to Earth's gravitational field dramatically. So today we have atom interferometers where we can achieve relative uncertainties in the sensitivity for accelerations. So delta G over G on the order of 10 to the minus 13 or so. So this is absolutely amazing sensitivities to relative accelerations. Of course, we also have gravitational redshift experiments, for example. Here's also one of my favorites by the group of Dave Vineland, where they have here an experiment where they have an optical clock built up on an optical table. They measure the frequency of the optical clock, and then they lift the whole table. You can see here, so this is just, you know, when you check up your car, they just did it with the optical table. they lifted it by 30 centimeters and saw a change in the frequency of the optical clock in accordance with what you would expect from a gravitational redshift. And there are many other experiments, many other examples. So for example, atomic interferometers now also have a sensitivity of Newton's constant, a precision of Newton's constants on the order of 10 to the minus 4. Only an order of magnitude shy from the fantastic experiments by the Washington group. And these experiments, so this is Guglielmo Tino predominantly from Lens, who is pushing here the frontiers and the boundaries, and they are closing in, and there's a good chance that they will overcome, they will supersede in precision the classical Cavendish type experiments soon. And also another example where you really have a beautiful connection between a genuine GR effect and quantum systems. There was a recent paper by the Kasevich group. Peter Asenbaum was the lead author here, where they showed that you can have phase shifts in an atom interferometer due to the curvature of the gravitational field, which is a genuine GR effect. So this is an effect that doesn't vanish when you go into a free fall configuration. So again, these are beautiful examples of experiments, and these are only a few, where gravity acts as a test mass in an external field. So what about now quantum systems that act as gravitational source masses? Is this meaningful? Is this realistic? Historically, I don't go into all of the details. There has been a wonderful recently published transcript of the Chapel Hill conference in '57. Most of you are aware of that. And you find there a discussion where Feynman also addresses the question how gravity possibly reacts to quantum systems. So the proposal was, in his words, one should think about designing an experiment which uses a gravitational link and at the same time shows quantum interference. So the idea was, here's the sketch. You have some sort of device that resembles a Stern-Gerlach type device, which allows you now to coherently take this ball here and place it in a superposition of either here, let's call it XU, or here, I exaggerate a little bit here, let's say a position here, which is then, so this is, no, sorry, so this is like XT for down, and this is a position XU for up. Again, this is our source mass. And imagine now that you have a test mass sitting here at a position X naught. And then you ask the question, so what happens when those two gravitationally interact? And what essentially happens is the two become entangled. So you start out with a state that it is initially separable. So you have the source mass in a superposition of X down and X up. It's coupled to the test mass at X naught. In principle, of course, you could now argue, well, you know, I also have to couple it now to the gravitational fields if you also want to take the fields degree freedom. But this is another discussion. So this was not done back there. And then you have simple Newtonian interaction between them. So you have an acceleration of the either up or down branch, right, which is simply Newton's constant, the source mass. And here you have the difference of up down minus the position of the test mass. Okay, and all of that you do, of course, while you assume that the superposition here is of macroscopically distinct states of the center of mass, which means that these two here, the scalar product of X down and X up, is in the is small, so it's close to zero. So it's macroscopically distinct, and this, of course, results now in an entangled state. So if you have now your down mass here interacts now stronger, so it actually lifts up the test mass to an upper position, and the upper one lifts the test mass less up, right, to a lower position, and this is entangled if also now our test mass positions are macroscopically distinct. So this is the argument. Okay? It's very simple. You somehow have gravitational interaction that can result then in entanglement if everything behaves according to quantum physics. So, and let's stick with that for a second. From a quantum physics point of view, this is super trivial. Okay, of course, you expect that the two systems become entangled. If quantum physics prevails at all of these scales and with these interactions, it's a totally obvious consequence. However, if you try to think of that phenomenon generating entanglement via gravity from a GR perspective, then it's anything else than obvious, no? Because from a GR perspective, any source mass configuration results into a fixed space-time metric in which the test mass will follow a geodesic motion. So that means once you are separable at a certain time t0 and you switch on interaction, then if the test mass follows simply geodesic motion, a fixed space-time metric, it will never become entangled with the source mass. Okay, so test mass geodesic motion, a fixed space-time background will always remain, will always result in a separable state. So the generation of entanglement itself requires that the space-time metric itself is also in a superposition. Yeah. And you, in essence, you find that statement here in this paper by Miles and Carlo. So basically, generating entanglement via gravity is inconsistent with any sort of semi-classical gravity approach. Okay, I need to hurry up a little bit. I hope I'm not too obvious with what I'm saying. I try to be brief, but slow.
You've been talking for 15 minutes. Yeah.
Okay, fine, good. So now, in a way, you can say, so Feynman has laid this ground with this Gedanken experiment, and back then already Witten. So Louis Witten, the father of Ed Witten, he was also present at the Chapel Hill conference. And he asked the question, what prevents this from becoming a practical experiment? And Feynman's answer is quite interesting. He essentially says, without saying it, but the way, I mean, from our today's perspective, he essentially says decoherence. Okay, so I think people like Zeh would have been quite happy to see this the way Feynman phrased it. So he really talks about information transfer to the environment and so on, which then basically will not allow this to happen. Anyway, now, if you look in the current literature, so for some reason, well, I think partly the reason was that the Max Planck Institute for the History of Sciences published in a brilliant effort together with many help of many people, published the transcript of the Chapel Hill conference, and this really sparked some interest. So I, for example, I was part of a working group at the Max Planck Institute for the History of Sciences where I became aware of that, and already back then, this I don't even recall it. This must have been almost 10 years ago or so. It was clear that there's an interesting overlap to these experiments, these current efforts of really having more and more massive objects in the quantum regime. So it was an obvious question then to ask, well, maybe 60 years later, is it now more realistic than back then? Okay, because at the Chapel Hill conference, there were two experimental questions that they were asking. The one was, do gravitational waves exist, and how to measure them? And the other question was, can we probe the quantum nature of gravity? So these were the two things that they were essentially talking about. The first one we ticked off after 60 years, and the second one we now basically are reaching it. So it's no surprise that then that everything now culminated, and then there were a couple of papers that took Feynman's Gedanken experiment and put some more concrete experimental proposal background to it. So there are two ways how you can think of trying to generate entanglement. The one is you simply take two harmonic oscillators and you let them interact with each other. Okay, so the interaction between the two results in a so-called XX coupling. So if you just do Taylor expansion here of this R-dependent interaction, you get an entangling interaction between the two, and the two oscillators become entangled. Yeah, so this is also the standard quantum physics textbook. What you can also do, now you go into the quantum information textbook, you say, oh, I make a superposition of two independent systems. So I have one mass in a superposition, the other mass in a superposition, and I start out in a bipartite separable state of these two, and now let them interact. I switch on the interaction, and now I have again a dynamical phase that this system acquires in the gravitational background of that system, okay? And vice versa. And then what happens is you now have a, since this is in a superposition and you have a phase shift there, you get a conditional phase shift. And this is equivalent the situation to a conditional sign gate in quantum information, C sign. So if you start off with two independent qubits, and you can introduce a pi phase shift that depends on the input of the qubit, so 0 or 1, which is here left or right, and this is what we have with the space, you can entangle them. So this is essentially, this is a C sign approach, C sign gate approach, and this is just a harmonic oscillator approach. Interestingly, if you do the math, actually it's a very simple derivation. You see that the entanglement rate for both of these scenarios, although they look quite different, is exactly the same. So the rate at which you generate entanglement between those two masses scales with G over H bar, the mass squared. So I now assume everything is degenerate. So the same masses, same frequencies, and so on and so on. So mass squared over distance times, and this is now the delocalization, which is in the harmonic oscillator case, the size of the wave packet. And in the C sign approach, it is the size of the superposition of the initial particles divided by the distance, and the whole thing squared. This is the rate. So it's the same here. It's just the meaning of the delta X is different. Even the meaning is the same. The meaning is the delocalization, and it's simply the practical implementation that is different. In the one case, it's a squeezing of the wave packet. In the other case, it's really a macroscopically distinct a separation of the center of mass in a superposition. Okay. Now, here comes the first question. Now we have the entanglement rate, and we require that this thing has to be large compared to the decoherence rates in the system. Okay? Intuitively, it's clear you cannot do that for arbitrarily small systems. Okay, and intuitively, it's also clear this rather be something that is on the order of seconds at most. Okay, so decoherence times larger than a second is something that, well, is nice, but quite unrealistic. I mean, even if you put a 10 there, okay, I might buy it, but let's say 1 second is something I can still comfortably sleep with. So let's ask the question, what does this mean? Okay, if this one is required to be on the order of 1. Good. Let's take a practical example. So let's take, for example, the distance between the two systems on the order of a micrometer. I think this is also realistic, because once you go even smaller than that, so because we're talking about the center of mass distance between the two, okay, you will have other forces that pop in, and you need to isolate gravity as a coupling force. So I think a micrometer is a safe thing to start off with. What about the delocalization with respect to the distance? Okay, so let's assume that. So just to be, so I just assume that now to be on the order of 10 to the minus 2. Okay, so I have a distance between my two systems, and I assume now that each of the system can be delocalized by an amount of, in this case, it would now be 10 nanometers. Okay, if I have a micrometer distance. If we use that, okay, then if you then compute now G, Newton's constant divided over h bar is on the order of 2 pi times 10 to the 23. Then we have 1 over d, which is 10 to the 6. We have delta x over d, which is 10 to the minus 4. And we have m squared, right? So this is approximately, now we have 6 times 10 to the 25, right? Times mass square. And this is supposed to, should be larger than on the order of 1, which means now that your mass square should be larger than 1 over 6 times 10 to the minus 25, right? Which is approximately 1.2 times 10 to the minus 13 kilogram square. And this is on the order of 10 to the 11 to 10 to the 12 silicon atoms. Right? And all of that is in a volume of d cubed, which is on the order of 10 to the minus 18 cubic meter. Right? All of that happens in it. So that means you see already what that requires now. It requires to have masses, masses here on the order. I mean, even if we okay, 10 to the minus 2 might be a little bit small. Let's say here, let's make here 10 to the minus 1. Then we have here 10 to the minus 2. Then we have here 10 to the minus 24, 27. Maybe that's minus 27. And then we have here 14. And that's then we are closer to 10 to the 11. And this means you can have a density of mass, okay, here, which is on the order of 10 to the 4 kilogram per cubic meter. This is a solid state object density, okay? So such a density you only get in solids. So if you take, for example, if you take atomic gases or so, okay, atomic gases have densities on the order of 10 to the minus 4, 10 to the minus 5 kilogram per cubic meter. Yeah, so there are like 8 to 9 orders of magnitude away from these densities. So you see where you would get. I mean, this is a square effect, of course. Then you would be at least 4 orders of magnitude away here in these requirements. If you don't have a solid, you have to have either incredibly, you have to push this to displacements that are insane, or you have to or you have to have extremely long coherence times. Okay, but now I really have to rush. I apologize. So the question is now, what about decoherence? Let's take some reality here, and I only give you essentially here the references. The main point is decoherence can be theoretically handled. It's understood. There's a master equation approach. So you basically describe this whole thing in an open systems dynamics. You know that there, for example, there are gas molecules. So the question is now, when your gas molecule comes, what is the de Broglie wavelength of the gas molecule that scatters? And for example, in the case for typical gas molecules that you have, the de Broglie wavelength is on the order of nanometers, even at a Kelvin temperature, which means that it's much, much smaller than any delocalization size that we are going to have. So it's the so-called short wavelength regime, which means a single gas molecule kick will just localize the particle immediately. Then you have black body radiation. Also, this you can compute, and I don't go into the details. I guess my main point is that you can identify many sources for decoherence, from gas damping to black bodies, scattering, absorption, emission. If you have a system like an harmonic oscillator, there's a trap fluctuates, which introduces heating rates, frequency fluctuates, which introduces heating rates. And then in case you really want to consider harmonic oscillators, then typically you have a link to the outside, for example, mirrors that are suspended. Then you have a damping of the mirrors. So you have thermal decoherence simply through the fact that you have dissipation in your system. So all of that you need to take into account, and then you reach a very discouraging table that shows you essentially what the requirements to date would be. If I would take, for example, a 70 nanometer glass sphere and use that as my solid state object, in order to generate entanglement at a pressure of 10 to the minus 17 millibar, which is feasible with a lot of technology, and ground state cooled particle, then you see I would need, and the ground state wave packet size here, okay, would be on the order of picometer. Okay, so 10 to the minus 12 approximately. So I would need here 2 micrometer delocalization of the wave packet and small temperatures. So I would need 6 orders of magnitude a larger wave packet than the particle size. Okay, so this corresponds to a squeezing of 60 dB, 60. I can go to larger masses, to a gold sphere. You see with a larger mass, oh, that's nice. I go to delocalization requirement only of 4 nanometers. But, well, of course, the ground state wave packet is also very small. Okay, so the squeezing is still 50 dB. And if I go to a LIGO mirror, the required delocalization is even smaller. But again, due to the extremely small wave packet size, in that case, femtometer size, I still have 60 dB squeezing requirement. And I don't know to date where we can go with squeezing. Okay, we have ideas. We think we know how we can squeeze wave packets to sizes larger than the object size itself. But if we will be able to get to such numbers larger than 10 dB squeezing, I simply don't know. The best values of squeezing to date is spin squeezing in atomic systems. And there I think the world record at the moment is around 30 dB, 30 dB of spin squeezing. So still three orders of magnitude shy of what we can have here. Now, this is my final point that I would like to make. If you still spare me like 5 minutes or so, I would like to go through the experimental aspects. Sure. So where are we right now? Is this okay, Marius?
Sure. Go ahead.
So here's my reality check. These are the 2 questions we want to address. How small can we make a source mass and still measure its gravitational field? Why is that important? Well, because in such experiments, we want to isolate gravity as a coupling force. If I cannot do that, I can only hypothesize. I can, in many of these short-range forces experiments, they hypothesize a possible Yukawa type term, for example. And basically, if they're not sensitive to gravity, they can only exclude parameter regimes for the Yukawa term, which are like 4 or 5 orders of magnitude larger than gravity. So you really want to, in particular now, if you want to entangle objects with gravity, you want to have gravitation interaction that is dominant. And then, of course, the second question is, how massive can we make a quantum system and still have long coherence time sufficiently long for our experiments? So let's stick to gravity briefly. So the smallest source mass as of a few months ago was like on the order of a gram. So let me just show you, we have recently extended this regime. So we went to smaller masses, and I will do that very fast now. What we did was essentially doing a small scale Cavendish experiment. Okay, so you see we have here our source mass, we have here the test mass. The idea is, let's stick here for a second. Here's the source mass, and the idea is that we modulate the position of the source mass as a function of time. Okay, and by modulating this, you generate here a time-dependent gravitational potential at the position of the test mass. So essentially, you have here here's a distance d naught, and now you change the overall distance. X of t is then simply d naught plus some modulation. So here this is 2 times the modulation here times cosine some frequency omega t, which then means, of course, that you get a acceleration of the test mass which is simply g divided by x of t squared. And if you again Taylor expand, you see you get a term that is proportional to cosine omega t plus cosine squared omega t, and so on. So you get in the response in the nonlinear gravitational potential is actually a linear response, quadratic response, and so on. Okay, and the parameters that we have is we have a source mass on the order of 90 milligram, 90, so it's 9 times 10 to the minus 5 kilogram. The distances that we have are on the order of 4 millimeter overall separation, and a modulation on the order of 1.6 millimeters. So the shortest distance between the surfaces was in the order of 400 micrometers between these. And so this means that the overall acceleration that we were sensitive to was on the order of 10 to the minus 10 meter per second squared. So this was the signal that we expected. I go directly to the results. I just mentioned in passing that we are extremely sensitive to everything out there. So to people on the streets, to street trains, even we estimated the Newtonian noise from the trams that were passing by our labs in 60-meter distance. So basically the gravitational noise due to the 90-ton Vienna trams that were passing. At the end of the day, here's the result. So what we saw is we observe now, so you can see here, this is the spectral response of the system on the right. So what you can see here is a linear response and the quadratic response. So we already see the higher order term due to the nonlinearity of the Newtonian potential that is produced from a 90 milligram source mass that we change here. So we resolve, I already showed you that, an acceleration modulation on the order of 10 to the minus 10, which means 10 to the minus 11 g at a precision of 1%. Okay, so we have a sensitivity in our experiment of 10 to the minus 13 g. And the systematic deviation that we have in our experiment is a little bit smaller than 10%. I mean, we have not corrected for that, but we can be sure that our interaction is actually gravitational. So this is the first. So we have now the smallest source mass to date is on the order of 100 milligrams. Okay? So it's still, which means now we are somewhere, so we push this regime to somewhere here. Okay, so this is already covered. Still, of course, now we want to go further. The next step is we want to go smaller than the Planck mass. This is our next experiment. We're already setting this up, which pushes us another 3 orders of magnitude in mass. Okay, so this will bring us somewhere here. Yeah? So we're getting closer. And now the question is, of course, what about this domain? And here what you see is the trend at the moment is the smaller the mass, here's mass, the larger the coherence time. So here are the beautiful experiments by Markus Aspelmeyer, for example, in Vienna, the molecular interference experiments, incredible coherence times and masses on the order of 10 to the 4 atoms, okay, in these molecules. And now there's this large bulk of mechanical devices, solid state devices with small coherence times. Now, what we are doing at the moment, and again, I leave now out all the details, we are trying to combine that. We use now solid state systems, but in a meta wave type configuration. And now, so basically in a free fall configuration. How do we do that? Well, we basically cut the support here of the solid and simply trap it in an external potential. So we have now a levitated solid state system with all the advantages that we can fully change the dynamic, the potential landscape here. So we can have the particle pretend to be everywhere. So this is like as if you would put now VR goggles onto your quantum system. Okay, so the quantum system just it sits in its trap, okay, in the cryostat or whatever, and you just change the trap while it still sits there. So you can do, in principle, you can have it go through a double slit, you can have it go through a Stern-Gerlach, while it sits in its directly trapped locally. So this is the idea, of course, the whole thing. How do we do that? We optically levitate. I spare you with the details here. Essentially, what we do is we have a microscope objective which focuses down light very strongly, and so it can trap a nanoparticle in the focus of the beam. And the whole idea is, since it's a dielectric particle, you have an induced dipole So the overall intensity here that the particle sees is nothing else than the inverted potential landscape. So if I have a Gaussian beam intensity beam profile, the potential that the particle sees is this negative Gaussian, which for small displacements is essentially a quadratic potential, harmonic potential. And this is true for all three directions because it's a focused Gauss beam. And so you have 3D confinement of the whole thing. What we do now is we trap the particle, we read out the position of the particle, and we do it in a way that we are essentially reaching the Heisenberg limit. So what we can do, we can now measure the particle with a sensitivity on the order of very close to the Heisenberg limit. So we can resolve the quantum ground state just by measuring it. So we can resolve the quantum trajectory of the particle, phase-space trajectory, with a precision of the quantum ground state, okay, or close to the quantum ground state. And which means that we can take the signal that we read out and we just feed it back on the particle position, stabilize the particle in its ground state. So what we have now is we have a room temperature glass sphere, 150 nanometers in size, carrying 10 to the 9 atoms, which is kept just by feedback in its quantum ground state of motion. Okay, and here's a picture of it. This is actually a picture of 150 nanometer glass sphere. It's kept in its quantum ground state of motion in a room temperature environment. Okay? So we cool it via feedback to its ground state, and then we take a picture. We have other methods of doing that. We also do it via cavity. So this is inspired by atomic physics. I don't go into the details here. Essentially, we used ideas from Helmut Rich and from Steve Chu and Vladan Vuletic from the late 1990s, where they suggested, or where they came up with methods how to laser cool molecules that don't have internal transitions, where you cannot do regular laser cooling. And the idea is quite nice. So you take the particle, your molecule or your particle, whatever, in a trap, an optical trap, and you put a cavity around it now. And the point is, you always have Raman scattering because the particle is moving. So that means you have contributions in the scattered light that take away energy from the system. And if you resonantly enhance now via the cavity resonance here, those scattering events, you can extract energy just by enhancing this anti-Stokes scattering of the particle. And just by placing the cavity and stabilizing the cavity frequency with respect to the tweezer, so the trap frequency, you can continuously cool the system down to its quantum ground state. And we did that. So this was an experiment we did last year. This was spearheaded by Uroš Stelic and was in collaboration with Vladan Vuletic at MIT, where we did that, exactly that. We placed a particle inside an optical cavity. We tuned the cavity resonance such that you resonantly enhance those scattering events that take away energy from the system, and then reading out the motion via so-called sideband asymmetry measurements. I spare you with the details now, but it had exactly the same effect. So in this case, we do not do active feedback, but it's the cavity that acts as a ground state temperature reservoir. So you cool the particle motion to the temperature, effective temperature of your cavity mode. Yeah? And this also leaves you with the ground state. And so we achieved now with this method also the quantum ground state in a room temperature environment. So we have that now. So this is actually, that's what we have in the lab. We can prepare the quantum ground state of motion in a room temperature environment of a 150 nanometer glass sphere. Okay? And now the question is, of course, now how can we get larger? Yeah? So we have now in the trap, we have a 3 picometer wave packet. And now how do we get the 60 dBs? How do we go from 3 picometer to 3 micrometer? Okay, I cannot answer that, but there's an obvious way, of course, what you could do, since now, you know, this is a trap, it's so nice, it's levitated, you can just switch off the trap. If you switch off the trap, you have free fall and you just have expansion of the wave packet while it falls. That's a very natural way. What you could also do is you could actually invert the trap potential. You can then have an inverted trap and you could have the wave packet exponentially increase its size in time while it goes down. Okay, so these are also possibilities. So instead of then in free fall having in 12 milliseconds an expansion to the particle radius, well, you can gain an order of magnitude, for example, okay, by doing it in inverted potential. So these are all tricks you can play now, and that we need to start playing. And then, of course, well, once we have that, we have written papers, and other people have written papers, how we can then go from something like that, so a ground state, to a really double peaked structure. Okay, but remember, it might not be necessary. If we just have very large squeezing here, this could also be sufficient just to see whether we can entangle via gravity. Okay, so this is just to say, you just need to believe me, we have ways, we are doing this at the moment. Mario Ciampini and Nikolai Kiesel group in Vienna has beautiful experiments where he changes actively the potential landscape that the particle sees. So we can go from a harmonic potential to a cubic potential to a double well potential to an inverted potential. Yeah, and this is now by my VR goggle example. Now we can make the particle ride the virtual landscape that it sits in. So here's an experiment where he generates a tilted double well and so on. And by the way, you could also have now a second particle, and you can start measure small forces between them. Okay, I mean, this is also a beautiful way to probe, for example, Casimir forces, Coulomb forces, and from very small particles at very small distance. Casimir of sub-wavelength particles very close to each other is something that also theoretically is not yet fully explored. Okay, so that's it. I know I took longer, but I hope that we have sufficient questions. Here's my summary. We have now in the lab, from a bottom-up perspective, we have entered the quantum regime of nanoparticles. We have now generated the wave packets in a quantum ground state. Our goal is, of course, now to generate either Gaussian states with large squeezing or non-Gaussian states with large separation. And on the top-down side, we have now measured gravitational fields of source masses as small as 100 milligrams. We want to go down now to the Planck mass as the next step. So this would be, by the way, I mean, this would be something like that here already. So this is our next experiment, a mass of that size, maybe that size. Okay, and then let's see. I mean, you see, there's still a gap of like 12 orders of magnitude between the two. But I think, well, I remain optimistic. Maybe. Again, I would like to challenge everyone. There must be other types of experiments that have a similar information content on what we can learn about the quantum nature of gravity out there. Thanks a lot.
Thank you very much, Markus. You had many ideas to talk about and many developments. So it's also justified the longer duration. I think it's super interesting. I will hold my questions because we'll have the chance to meet also probably, and go to the people that have raised hand. I think first was Alexei, and then it's Carlo. Alexei?
Yeah, well, thanks, Markus. Yeah, this is great and very inspiring. I have a quick question concerning the experiment in which you are comparing the decoherence rate with the entanglement rate, and then with this quick calculation you showed what kind of masses we need. You're talking about bipartite entanglement, right? Will it change something? You know, we can have maybe 3 of such particles and talk about GZ. We can even maybe have a cluster with some kind of, will it change something in your calculation if you don't take just 2 entangled particles, but somehow enlarge that?
Yeah. So quick answer, I don't know. Let me just, so first of all, I think going to more particles is definitely then it's a more subtle configuration. And I could very well imagine that maybe because, so what you could do, for example, you could basically, instead of measuring directly entanglement, you could also measure the loss of entanglement, for example, 3-parted entanglement. Okay, so let's say if you entangle 3 particles, for example, with each other, and then switch on generation, then switch on gravitational interaction, because of monogamy of entanglement, then you should start losing. You should start losing one type of entanglement. No, so maybe with a monogamy argument, you could have another witness of the interaction that is then more susceptible to it. Yeah, I think the idea is a fantastic one. We have not yet really worked that out, but we are looking into other entanglement witnesses, and on the other hand, maybe it's enough to have some coherence witnesses. No, maybe you do not even have to look for entanglement, but just have to ask whether there's coherence or not. And I'm not sure whether this is the same. On the other hand, of course, okay, last comment, Alexei. Of course, you're also susceptible more strongly to environmental decoherence again. No, if you have you know that GHZ is a extremely susceptible to the environment.
Thanks. Thank you, Markus. Yeah.
Thanks, Alexei.
Carlo?
No, sorry, I was just clapping hands. Maybe I pushed the wrong button. So
yeah, and I appreciate that. Yeah.
So let's the other go ahead.
Pierre?
Yes. Hi, can you hear me well?
We can hear you.
Okay.
A little bit
So,
interrupted, but okay.
Okay. So first of all, thank you for a very informative talk. My question is about your experiment with the small Cavendish balance with the gold sphere. I was wondering whether you were actually measuring the gravitational constant in this experiment, and if so, what was the precision that you were able to reach?
Yes.
The general motivation for this question is I'm wondering whether we are getting more precision by making small Cavendish balance, or whether we are getting more precision by making big ones.
Thanks. That's a fantastic question. So firstly, note, so this experiment was not specifically tailored to be very precise. So the idea of this specific experiment was really to see the effect. Yet still, let me just go there. So here. Yet you can see that the accuracy with which we have measured that was 10%. So we have measured the coupling strength with an accuracy of 10%. Okay, and the precision of the measurement, so the precision of our acceleration measurement was even 1%. So remember, I showed you the precisions of the experiments by Gundlach and Edelberger. The large Cavendish, they got down to 10 to the minus 5 precision. So here we have 10 to the minus 2, so they were 3 orders of magnitude better. And the atomic fountain experiments, they used, I think, also a few 100 kilogram source masses. Or some tens of kilogram source masses, they were at 10 to the minus 4, so 2 orders of magnitude better. With this type of configuration, when we slightly increase, so when we go here from, this was a millimeter source mass, when we go slightly larger, we have already conjectured that we can reach precisions that are comparable to the current experiments. And the interesting part is that this is simply a different way of measuring it. It's a different regime of measuring it. In principle, we could go even to larger frequencies here, because the big problem of these measurements is systematics. Okay, so I don't know if you're aware of that, and I'm not sure that I don't have the plot here, but there's this big problem with measuring Newton's constant, that you have better and better experiments, so in which the precision becomes better and better, so the error bar becomes smaller and smaller. However, the accuracy of different experiments differs by more and more standard deviations. So basically, you have data points here, here, here. If this is G, and now in previous times the error bars were sufficiently large that they overlap, and now the error bars of these experiments become smaller and smaller, and they're not overlapping anymore. Okay, so you have now basically the experiments fall into two categories: one on the right side of the co-data value, and the other one on the left side of the co-data value. So Guglielmo Tino told me that when they published their experiment, he suddenly had a well-defined number of more friends, which were all the ones that were on his side of the co-data value. And so there's currently in this community, there is an effort of getting rid even more of the systematics by, for example, swapping experiments, putting an experiment to another location where another team actually does the experiment with the other system, and also coming up with other experimental geometries where you have other systematics. And going to small source masses is actually one example of having other systematics. So I would say it's not fair to say that we will be significantly better going to smaller masses, but we will be significantly different going to smaller masses. And I think this is relevant for understanding where this discrepancy in the big G measurements comes from. This is one of the unresolved questions in big G measurements.
And people are quite confident that this discrepancy is coming from systematics.
Yeah. Well, also, I'm just looking for one slide where I can just I don't have the slide here, unfortunately. I will look for it in a second. But actually, there's a very famous plot where people put here the value of G, and here the mass of the source mass. Okay, this is the logarithm, right? And basically what they get is they get a number of data points here, right? And what they do is they fit a line with a non-zero slope through it. Yeah, and I think once people do that, they are desperate. Okay, so who knows? I mean, right now we are really somewhere here. Okay, so we really are many orders of magnitude on the other side. So if there were something to the non-zero slope, which I doubt strongly, then with a smaller error bar, one could set another data point here. Yeah, but honestly, if you look at the system, these are huge experiments, huge masses, and it's already the biggest problem is knowing the center of mass of such a large sphere. You have density inhomogeneities, you have temperature fluctuations where then the thing drifts and so on. So it's amazing that they are so precise.
Thank you.
All right. There is a question in the chat before we move to the people that raised hand. Could you say something about the prospects of testing the Ozzie-Penrose type objective reduction models?
Yeah.
Donald Salisbury.
Hey Don. Thanks. Yes. So to put it, I go back to this. I go back to the here where I put up the result from Marius and Carlo. So let me make it as blunt as possible. So these gravitation-induced collapse models that are out there, they either directly or indirectly fall back to this idea of semi-classical gravity, namely that somehow the gravitational field is sourced directly by the different branches of the wave packet, so that different components of the wave packet do have direct gravitational effect. So that means, as a consequence, that if we were to generate entanglement through gravity, we would immediately falsify the underlying assumption of these models, like DOG, Penrose, and so on. So in that sense, it would be an I claim strongly ultimate test for those.
All right. The next is Marco Vojinovic.
Okay, thanks for the talk. I liked it a lot. My question is about all the experiments basically that you described so far. How hard is it to remove the electromagnetic effects? You want to shield for electromagnetic in order to see what gravity does. So how hard is it experimentally to actually perform that, and how does it scale with the mass of the particle? I mean, I assume that for larger masses it is easier to shield for electromagnetic effects because they cancel sort of gravity accumulates. But can you tell us more about that?
Yes. So there are two answers to that. Number one, for the gravity experiment that I showed, we, as you can see here, we used a Faraday shield. Okay, and so there was essentially a gold shield here between the gold-coated aluminum shield between those two. Yeah. So the whole point of the Faraday shield is, and this is the whole trick of the experiment. You see that we modulate the source mass. Okay, so we have a time-dependent gravitational field here. Okay, on the test mass that is not shielded by the Faraday shield, but what happens? The effect of the Faraday shield on a modulation here on one side is that it produces a non-modulating static DC force here. Okay, so when you change the position here of so let's assume those both are charged. Okay, if you change the position here, then because of the Faraday shield, because you induce here the mirror charges, you don't change the static interaction here between them. You will always have a static interaction between the shield and the source, but you will never get a time-dependent interaction. So the Faraday shield actually generates a DC bias. So there is an additional. So we have in this experiment, for example, we have on the order of 10 to the 4 charges on the sphere. Okay. So this one is grounded. So this one you can ground. But here we have on the order of 10 to the 4 charges. And the point is now that the Coulomb force between, or the electromagnetic force between these two, because of the Faraday shield, is distance independent and therefore time independent. So we can discriminate the time dependent gravitational force from the static electromagnetic force in that case. And this will always be true for the Faraday shield. So if you have, so you win when you look at the fluctuations, okay, and not at the DC component.
So you cannot eliminate the electromagnetic field, but you can see the difference in the data when you sort of compensate for it, right? I see.
Yes, because this is exactly, because this is DC, so it's just a bias, okay, that is constantly there. And on top of this bias, you have the gravitational modulation.
I see.
And if you go now to the levitated particles, okay, so the small particles in the levitation case, we can get rid of all the charges. This is because they're levitated. This is so nice. So the problem with the Cavendish is that it's connected to the outside world, and it's super hard to remove all the charges. So we used actually methods from LIGO. So we had nitrogen gas, ionized gas that went through and so on to remove as many charges as possible. But it was hard to push it below 10 to the 4. Here on the levitated particle, we actually have electrodes here so here close to the particle, where we can measure the charge. We can ignite a plasma close to the particle, and we can have charge transfer to the plasma, and we can actually see that we can transfer individual charges, and we can reduce the charge to exactly 0, and then switch off the plasma, and then have a neutral particle. I mean, the problem is not fully solved because it's a dielectric particle, so you still have some internal dipole moment due to defects in the particle itself. Okay, so these are things that David Moore and Giorgio Gratta at Stanford and Yale have measured. Yeah, and they are sensitive to these dipole moments. So you cannot fully get rid of them. You could, for example, average them out. So Giorgio is actually rotating his particles in order to average out the effect of aligned dipoles interacting with each other, which is really brilliant. Or you could, again, just put a Faraday shield to get rid of those. Okay. But that's a nice thing about levitated systems. So this is why we also want to push our gravity experiments towards levitation, because you have this full control over everything.
Excellent, excellent. Thank you.
Thank you. Alexei, yes, go ahead, please.
Yes, back to Markus, I was just talking here with a colleague, and back to my previous question. I understand what you said, that GHZ would be probably very difficult to use because of a very short decoherence time for GHZ. Maybe as a quantum signature, as a non-classical signature, we could go the other way around. That is, use quantum contextuality and use one system, because that would give a longer decoherence time. So quantum contextuality has been measured on ions in traps, so trapped ions. Maybe if we could use gravity to destroy quantum contextuality of a trapped ion, that would give a much longer decoherence time, because there is just one massive system.
I like that. I've never thought about that. This is I like it very much. Thanks. Yes. I see. So we are trying to now create some sort of witness, no, for the impact of something out there.
Yeah, some quantum witness that this is really a quantum system, and then use gravity and see how it destroys that quantumness, if it does.
So due to entanglement in that case, right? So this would you would still
entangle. Well, if we have one system, it will be contextuality. So probably to probe contextuality, you need to do sequential measurements very quickly, and during that time, if you turn on gravity interaction, it may actually break that contextuality.
Yeah, what I'm saying.
I'm inventing. It's just just an idea.
No, what I'm saying is, in order to break contextuality, what you would have to do is you would again have to generate entanglement between the gravitational source and the particle.
Oh yeah, absolutely.
So, yeah, exactly. Okay, well, that is that is very good.
But maybe that would give you a sufficiently long decoherence time. Of course, we need to compute that.
Yeah, but now the situation didn't change. No, I mean, we're now back to having to entangle the two systems, so we are fighting again entangling rate versus decoherence rate. And it's the decoherence rate again of the entanglement, no? Because you need to generate entanglement in order to lose contextuality at the probe.
Let me think about it. Maybe is there no way around? Yeah, okay. So maybe we should give the floor to somebody else. But yeah, let me think.
Yeah,
about it.
But just let me comment on one more thing. I think we went in our first question. We went even further. Because I think we also turned the argument around that we could start with entanglement,
and then destroy
two systems, and then you have the third system that enters, and through entangling now with those two, destroy the entanglement of the two. Right. So
yes,
and maybe this could be a more subtle probe. So it's something that
maybe you're right. You're right. Yes, but then the coherence times need to be really. I mean, you need to act very quickly, because if there's three-partite decoherence,
exactly.
they go too fast. Yeah.
Yeah.
Okay. Okay. Thanks. Yeah. Thank you.
Thank you. Martin Green.
Hi, can you hear me properly?
Yes.
Good. Very interesting talk. Thank you.
Thanks.
Two questions, I guess. The first one to pick up on this this electromagnetic screening. The question is whether the Faraday shield shields against van der Waals type effects. We're talking 40 orders of magnitude between electromagnetic and gravitational, and so even a van der Waals effect could be significant.
So the short answer to that is yes, because we still have a lot of atoms in there. No? So there's still Avogadro is still it's you still have number of atoms squared that enters if you do the comparison with the 40 orders of magnitude, which is the electron mass, right? More or less, it's the it's always a sort of unfair comparison if you now have these still comparable large objects. We did the only thing that we did at the moment is we did simulations. Okay, but yeah, you're right. At some point, you are going to hit the situation where the magnitude of the fluctuation in acceleration due to gravity that you induce will hit the noise floor of your of your Faraday shield's capabilities. Yeah, I do not have a number here yet for you where this would be, but I assume it will be mechanical noise of the shield and thermal noise of the shield that will be then the limit. Yeah.
Okay, but the van der Waals effects between the test sphere and the driving mass, those effects are ignorable?
Yes, they are ignorable. At the moment, you also have to bear in mind we have at the current experiment a distance between the surfaces of the two masses on the order of 400 micrometers. So this is still several orders of magnitudes larger than what would be required to for van der Waals to start taking into effect.
Okay.
I think I estimated that this on the 1 micron scale, I think these effects should start to dominate.
All right. So the second question is really it's more of a comment, but if you take the semi-classical gravity approach, there's a premise in there, implicit in the semi-classical Einstein equation, that the geometry is actually well defined. But one could look at this and say, well, the right-hand side has quantum uncertainty. There are fluctuations, and the expectation value of the stress energy tensor is not a nice C number. That there are these fluctuations, and those fluctuations, quantum fluctuations, result in the geometry itself being classically uncertain. And that uncertainty then means that the geometry is just not sufficiently well defined in order to be able to resolve the superposition that you're trying to look at. So it's just a different way of looking at this semi-classical gravity. To think of geometry as being classically uncertain, with its source being the uncertainty of the quantum state.
Now, a question from my side to the comment. Wouldn't it still mean that semi-classical gravity cannot allow for the creation of entanglement through this type of interaction?
Yes, I think it would, and certainly if you could demonstrate entanglement, then that would be a very interesting result, and would be significant from that perspective.
Yeah, but I fully agree with the comment. Yes, thanks.
Thank you.
Thank you. Are there any other questions? I don't see any hands raised, I think.
Andrea has a question.
Oh, Andrea, go.
Hi, thank you for this talk. It's amazing to hear what it's actually possible to do in the lab.
Thanks, Andrea.
And I wanted to ask you, as you know, the original proposal from the Bose et al. Paper proposed to put the masses in a superposition that is entangled with the spin that is embedded inside the nanoparticle. So when you have the two superimposed particles, and from what I understand, in the lab you're exploring doing the superposition just allowing the wave packet to split into the bottom of a well, essentially. So you're not thinking of using this, like some spin-dependent forces to delocalize the particle. Just allow it to delocalize.
No, that's certainly also possible. So I think we are now at the stage where we need to explore many possibilities. Okay, I mean, definitely an internal degree of freedom is a very attractive way of doing it. At the moment, I fell in love with our ability to manipulate the potential landscape. So I guess I still need to understand what we can do with that. So this is something I would like to see how far this brings us. But certainly, no. So everything is on the table right now. So everything that brings us there is a valid approach, definitely.
And just as a quick follow-up, so maybe this is a naive question, but how do you measure the entanglement if you just have this the particles just in two different positions? Like, sorry, if you have the particle just delocalized, how do you measure its entanglement with the other particle?
So for the oscillator case, for example, the entanglement would be in momentum and position, right? So what you would need is, do you still see my slide?
I see.
Yeah, what you would need is exactly what we are doing here, right? So what we are doing here is basically we have a second. There you go. So you see, we have the laser that hits the particle, and then we read out X, Y, Z. This is now, to be very fair, this configuration is not the good one, but we can have a configuration now in the back plane. This is where I said we now have a quantum limited position measurement, which essentially means we have a low noise measurement of the position and momentum. So we can track the phase space. And this we can now, this is a so-called homodyne measurement, where we essentially measure, where we, out of the amplitude and phase fluctuations of the light that we measure, we can directly convert that into position and momentum information of the particle. And this you can do now with both particles. And this is a standard way from quantum optics, how you can then infer entanglement.
Right. And this is for the vibrating particles.
Yes, exactly.
What about the ones that are in superposition of positions?
Well, in that case, the suggestion was that you use an internal degree of freedom, for example.
All right. Right. So in that case, you would have to use it.
No, well, let's say this is the most simple way. You know, on the other hand, once you do have a method to generate the superposition, okay, then you have also a method to undo the superposition. Okay, so you can think of it in that way, that basically the method of doing the superposition is your Hadamard gate that creates the 0 + 1. In the Bose case, it's the spin degree of freedom in a Stern-Gerlach configuration, okay, which is essentially what Feynman was proposing. You have the superposition, and then of course you just invert the Stern-Gerlach and have an interferometer. But if we find some other way to create the superposition, then we also just invert that, and then we have this.
Okay. Thanks.
Yeah.
Thank you. If I may follow up on what Andrea is asking, I would also like to get a bit more understanding of the ideas. So the levitated particle is yet another possible realization that you mentioned. And I honestly did not understand a lot what is going on with the virtual. You were saying something about the virtual.
I see. Okay. Yeah.
You could, yes, elaborate a bit on what's happening there.
Okay, let me make an historic comparison. Okay, and this is not to scale, just for understanding. So take a Stern-Gerlach experiment. Okay? So the power of the Stern-Gerlach experiment and the experimental power that in particular then Stern used later was to have as well prepared molecular beam as possible and have as long magnets as possible. So basically the art of the whole thing of measuring then even nuclear spins, what Stern then received, got the Nobel Prize for, was in having experimental capabilities of extremely long molecular beams and long magnets for deflection. Okay, molecular beam method. This was like the power of the Stern-Gerlach experiments. Then came Rabi. Okay, so it was essentially with Rabi's insight that you could then take the whole Stern-Gerlach idea and put it in a glass of water. And instead of having the molecules follow a beam, right, and going through the Stern and going through the physical magnet, the molecules were sitting in water, which is sitting there, and they were experiencing a time-dependent magnetic field. From the reference frame of the molecules point of view, it doesn't make a difference. It doesn't make a difference for them whether they actually physically fly through the magnet or whether they sit in their glass of water and experience a time-dependent magnetic field. Okay, and so and this is exactly what you have today when you buy your Oculus Rift virtual reality goggle. Okay, so you don't have to go to the roller coaster anymore. You just go at home into your chair, you put on the VR goggle, and then you ride the roller coaster. And oh, I tell you, I mean, this is a frightening experience. I recently started that, and holy moly, you stand on top of a building that's 300 meters high, you look down and you know you're standing in your office, okay? And there's everything, you can go everywhere, and you do not dare to make a step forward. You just don't. And so there's no difference. So this is what I mean. So instead of now having free fall experiments with massive particles over long distances, you just have the particle in the trap and you let the potential landscape come to the particle. Instead of having the particle fly through the double slit, you have the double slit come to the particle as it sits in your lab. Okay, and then look at the consequences there. So this is what I meant.
Okay, but so naively, just a quick follow-up. How do you, so okay, I think naively what's going on is that you split the wave function, right? Without actually moving the center of mass. But how is it, so if there's a magnetic field, there is going to be an internal degree of freedom that is manipulated, a spin.
So how do you do it without it, you mean? Is that the question?
Yes, is there an internal degree of freedom that is quantum manipulated, or?
No, you don't have to. So there are a couple of, so yeah, okay, yes. So I very quickly went through that. No, I mean there are, and again, so you see, this is a paper we wrote almost 10 years ago together with, well, actually 10 years ago, I can't believe it, with Oriol Romero Izard's team, where we were suggesting how you could do. So this is essentially, it's done through measurement. Okay, let me do it very easy. It's done through measurement. So you prepare your particles somehow in a coherent state, in a pure wave packet, and then you try to produce an intelligent measurement on the system. For example, if you have here a well delocalized state, let's say with delocalized, here is the x-axis, here 0, okay, and you manage somehow to do an x-square measurement. Okay. Then actually for the particle, it doesn't matter whether the x is a plus x or a minus x, no? Because it's an x square. So it means the result of the measurement will actually be a doubly peaked wave function. Okay. There are some caveats depending on how you realize it. So back then we had previously with Michael Wenner and Chad Milburn and Myung-Chee Kim, we had introduced this idea of pulse optomechanics, where very short pulses can be used to have to create really projective measurements type on a system. And so we combined that in this paper to show that with such a projective measurement, you can also have a projective x-square measurement. And the only problem was that you could not define deterministically what then the distance of the splitting would be here, this one at delta x. So actually you would get every value, every possible value. You would know which one you get, okay, but you would have to post select on a sub-ensemble that always had the same value. So it's not a super efficient one, but it's okay. Yeah, so this is a way. And here Romero Izard's group then suggested a little bit later similar things with a magnet, where a small magnet was actually going through a potential landscape, a magnetic potential landscape, and there they also had a combination of free fall in inverted potential, and then here an X square measurement that then channel. You see, you go from here, this wave packet, to the double peak through an X square measurement, which was in that case by coupling to a qubit. So you need some sort of strong measurement on the system. That would do the job, for example.
I see. Thank you. Thank you very much. Carlo has raised hand. Carlo, go.
Yeah, this time, am I muted? No. This time was really his hand. So first a comment, and then a clarification. The comment is that I'm very happy of Markus. I was very impressed. I mean, of course, I'm a theoretician. So every time I see what you guys can do, I'm just, it's totally amazing. But it's not just, I mean, I was impressed by the sort of conceptual clarity of everything you were presented. It was very comprehensible for me. And also the historical part was very useful for me because I didn't have the history of this, of how we got to this, and in fact, it reoriented my thinking quite a lot. So thanks a lot. Now, there was a question about the Penrose sort of hypothesis of the gravitation-induced collapse, and I understand your answer. And in fact, I think I completely agree. It was clear, but I would like to see just a little bit more clearly. The semi-classical gravity hypothesis, which is perhaps a little credible for other reasons, or it could be, but it's certainly different from Penrose, and is definitely ruled out by gravity-induced entanglement, obviously, for the reason you said. The idea like Penrose or those based on that, of course, it's not semi-classical gravity, but it's similar, as you said. It's just a sort of in between, because the gravitational field can be in a quantum superposition, but not too much. That's Penrose's idea. Somehow there's some nonlinearity in the unitary evolution. It's not unitary. It's not linear. Which brings it, and as you said, it brings it exactly back in a sense to classical gravity, because macroscopically then gravity is, and there's a clear idea of where this happens, at least in Penrose's original intuition, which is sort of the one graviton threshold. This is Planck mass. There's an actual parameter there. That was Penrose's idea. So it's not by itself, it's not a parameter-free idea. Now, are you saying that now? So all this much with what you're saying. Now you're saying those experiments will rule it out, which seems very plausible to me. But would you rule it out because somehow, in principle, the Penrose scenario would allow superposition and therefore gravitational gravity-mediated entanglement, but only to a level that, and this is a question, necessarily would be invisible, or in the actual experiments that we're considering, we would be beyond the threshold where the Penrose collapse has already happened. I don't know. I didn't say it clearly, but I think you.
No. I understand totally what you mean, and
okay.
I have an intuition, but not not an affirmative direct answer because my intuition would be the first one, meaning that it cannot, in principle, be possible to generate it. However, this is this is just a feeling based on what I said before, no? That that I really think that the underlying principle, this whole idea, you can rephrase somehow to this idea of semi-classical gravity. But it might even be, and this is super possible, that someone out there has already written a paper on that and it's already in there. But at least I'm not aware of it. So certainly the second case that you said is certainly true. So that the parameter regime we're operating in is certainly such that you will
outside.
Is well outside the regime. Okay.
Yeah.
But this is an interesting challenge. Okay. So I dare say that if you try to write it down, then there must be a general no-go condition somehow. Yeah. I'm quite confident this must be the case. I haven't seen it, I haven't done it, but intuitively I would be super surprised if it would be if it wouldn't be more than a practical argument. That it has to be an intrinsic argument.
If there was a window of possibility, nevertheless. I find this reasonable and credible. Thank you, and very clear. Thank you very much.
Yeah, thanks a lot.
Great. So if you have any more questions, please feel free to unmute and ask or comments. No? Okay, so in that case, we can thank the speaker. Thank you very much, Markus, for the very interesting talk.
Thanks a lot, and also thanks for this setting. I have to say, from all the Zoom meetings that I do with decreasing motivation, this was by far the best one, because I really enjoyed the intensity and length of the discussion. Thanks a lot. Great. This is a perfect format.
Thank you very much.
And it was great seeing everyone, really. And you all have a standing invitation to Vienna. We need to make that happen.
As soon as they open the cages and let us travel again.
Exactly. Yeah. I will sit down with Czeslaw next week, and we will come up with a plan how to revive our discussion culture again in Vienna.
Yeah, sounds great.
Very good. Okay, all the best.
Everybody.
Bye.
Bye,
everyone.
You.
Bye. Thank you, Markus.
Bye.